Hello everyone and welcome back. Okay, so right now we are discussing about precipitation hardening, which is one of the other strengthening mechanisms that you have in aluminium alloys. And in the previous class, we have talked about the basics of this particular phenomenon. And then we have also seen the three steps which are involved in precipitation hardening. And these are solutionizing, followed by quenching, and then finally aging at a particular temperature. Right, and what happens in each of these stages, that is what we have started discussing in the previous class. Solutionizing is the stage where all the solute goes into the solution when you hit it to the single phase region. And then when you quench it with a high cooling rate, it becomes supersaturated at room temperature. And when the aging is done at a particular temperature, this excess solute that you have comes out as precipitates, and that's what gives you the hardening. Okay. So to proceed, I would again like to go back to these two diagrams. One is the phase diagram, the equilibrium phase diagram, and the other one is the TTT diagram. Okay, so what we discussed in the previous class is that when you cool at slow cooling rates, after hitting it to the single phase region, then it will go through both the start as well as the finish curve, and you will get this equilibrium phase, which will be coarse in nature. On the other hand, if you cool it down fast with a high cooling rate, then you can actually avoid the nose of the TTT curve, and as a result of that, you will get fine precipitates. So this is the equilibrium condition which is maintained here. So it's cooling through this particular temperature range from Ts to Tn, and then as you go below Tn, the transformation to the theta phase or the equilibrium phase starts, and as you go below this and continue to cool it down, then at a particular time the transformation is completed. Okay, so that is the point over here when it reaches the finish curve. On the other hand, when you cool it down fast, this equilibrium transformation does not take place, rather you will get a supersaturated solid solution, right? And when we age this supersaturated solid solution at a particular temperature, you would get this fine precipitates. Okay, and then we had started discussing about the mechanism as to how this strengthening occurs when you have this precipitation occurring in the alloy. Okay, so there are two cases depending on the temperature of the aging. One is the natural aging case, where it is aged at room temperature. And the other one is artificial aging, when the aging is done at an elevated temperature. Okay. So here, in case of natural aging, when you hold the alloy isothermally at room temperature, the excess solute that you have in the solution will come out as cluster of atoms. On certain planes. And these clusters are known by the name Guinier-Preston zones. Or GP zones. Okay, and the atoms which are now forming as clusters in these GP zones are the solute atoms which are different from the parent atoms, right? For example, if you talk about the aluminium copper system, this will be the cluster of copper atoms. Which are quite different from the parent aluminium atoms, and therefore there will be certain mismatch between the GP zones and the parent matrix, and that in turn will create some lattice strain, and as a result of that, the movement of dislocations will be hampered and the strength will increase. Right, so this is what we have seen in the previous class also, that the strengthening in case of natural aging occurs due to the formation of GP zones only, and the precipitates are yet to form in this case. Okay, so now let us go to this artificial aging and see what happens here when the temperature is higher. Okay, The precipitation in this case occurs in a sequence, and depending on what phases are forming in each of these stages, you will get a particular hardness. Therefore, you can plot the hardness as a function of time, and from this you can actually see the sequence of events or the sequence of precipitation as it occurs during the artificial aging process. Okay. This would depend on the alloy system as to what will be the exact sequence of the precipitation phenomenon. That will depend on the alloy system. So as we increase the time, the hardness would also increase. Then it will go to a peak, and beyond that it again starts to decrease. Okay. So in the beginning, as we have seen, the GP zones will form, and these are basically the cluster of the solid atoms as we have discussed. And then depending on the alloy system, you might have another intermediate phase in between before you go to the precipitate. Okay. So we can again take the example of the aluminium copper system. So in that case, as you progress after the GP zones, there will be one more phase known as theta double prime that will form before the precipitate theta prime forms. Okay. And sometimes this theta double prime is also known as GP2 zones, and therefore the first GP zones can be also called as GP1, right? So when the precipitate forms, you will get the maximum hardness, that is the peak hardness, and this condition will be known as the peak-aged condition, and this is what is indicated by this T6 temper that we discussed before, right? So in a particular alloy, the precipitation occurs in a particular sequence, as you could see from here for the aluminium copper system. Okay. So now if I want to write it as a sequence of events, then we can write in this manner. You start with the supersaturated solid solution, which is obtained after the quenching operation, and then as you age it, first the GP1 zones will form, followed by the GP2 or theta double prime, and then the precipitate theta prime forms. Okay. And as you go beyond this, then the equilibrium phase theta will form and the hardness will come down. Okay. So this will happen on prolonged aging or overaging when the equilibrium phase forms, right? Now we need to understand as to why this theta double prime or theta prime gives rise to an increase in the hardness. Okay. So as I said before, these GP zones are basically the cluster of the solid atoms, and since these atoms are different from the parent atom, there is a lattice mismatch. And this will result in some lattice strain. And as a result of that, the hardness and the strength will increase, because now the dislocations will find it difficult to move through the strained lattice. Okay. This is same as the theta double prime also, because now the GP zones will grow and this theta double prime phase will form. So that is also is different from the parent metal in terms of the lattice and the atomic arrangement, and therefore it will also give rise to lattice strain and lead to an increase in the hardness, right? The same goes for this precipitate theta prime. These kind of precipitates are known to be coherent precipitate, meaning that this will try and match with the lattice of the parent metal. Okay, although their lattice is different from the parent, because this is a different phase altogether, but they'll still try to maintain a coherency with the parent matrix, and therefore it will create some kind of strain around these precipitates. Okay, so that is known as coherency strain. So now in terms of the dislocation mechanism, same thing will happen. The dislocations will find it difficult to move because of this presence of the strain in the lattice, and therefore the hardness and the strength will increase. Okay, so this is one of the mechanisms of the precipitation hardening as to what exactly happens that ultimately leads to an increase in the strength. Okay, but this is not the only one. There are other mechanisms also, like how we had seen before for the solid solution hardening. Here also there are certain other mechanisms that you need to look at, right? So in case of solid solution strengthening, we had to look at the interaction between the solid atoms and the dislocations. Here, instead of the solid atoms, we have the precipitates. So we'll have to look at the interaction between the precipitates and the dislocations, right? So one of them, of course, coming from this coherency strain, when the dislocations will find it difficult to move through the lattice due to the presence of this kind of strain as a result of lattice mismatch between the precipitates and the parent matrix. Okay, and the strength increment delta sigma due to this is given by the following equation. Where epsilon is the lattice strain associated with the misfitting solute atoms. R is the size of the precipitate particles or the radius of the particles. And F is the volume fraction of the particles. Other terms have their usual meanings. G is the shear modulus and B is the Burger's vector of the dislocations. So that is one of them. The second one comes from the stacking fault energy. I'll come back to this and elaborate as to what exactly it means and how it happens. Then here also you have the ordered structure hardening, like what you have seen for the solid solution strengthening. Here also a similar mechanism will occur due to an ordered structure. The fourth mechanism of strengthening in this case is the modulus effect, and this is again similar to solid solution hardening that we have discussed before. The fifth one is about interfacial energy. And the last but not the least, we have something called lattice friction as another mechanism of precipitation hardening. Okay. Lattice friction stress. So let us discuss each of these mechanisms one by one and try and understand them. Coherency strain we have already discussed, so let us go to the second one, which is stacking fault energy. This is due to the fact that the stacking fault energies of the precipitates and the parent metal are different. Okay. And this is basically due to a local variation in the stacking fault width. And as a result of this, the dislocations will find it difficult to move through the precipitates. Okay. And the strengthening that you have due to this effect, delta sigma, is given as follows. Okay, so this is given by this particular equation. Here, the term K alpha that you see, it is a product of the force separating the two partial dislocations and the distance between them. Okay, so we have seen the stacking fault is created when a dislocation is split into two partials, and in between these two partials you have the stacking fault, right? And the stacking fault energy also depends on the width or the distance between these two partials, right? So this K alpha term is the product of the force separating the two partial dislocations and the distance between them. The other term that you see, that is F1, is a complex function of stacking fault width and the precipitate size. And small f is the volume fraction of precipitates. Right? And the rest of the terms that you have their usual meanings, like, here B is the Burgers vector, gamma m and gamma p that you see over here, these are the stacking fault energies of the matrix and the particle respectively, and E is the elastic modulus. Okay. So this was about the stacking fault energy mechanism of precipitation hardening. The next one is ordered structure hardening. This is similar to what we have discussed before for solid solution strengthening. And we have seen that when there is an ordered structure in the lattice, the movement of dislocations through the ordered region creates what is known as antiphase boundaries. Okay. So if the precipitates have ordered structure, then the similar effect will come over here also. Antiphase boundaries will come due to the ordered structure, and we have seen that movement of dislocations through the APBs is difficult. And as a result of that, the strength increases. And the strength increment in this case is given by this particular equation. Where gamma APB is the antiphase boundary energy, R is the size of the precipitate particles or the radius of the particles, and F is the volume fraction of the particles. Okay, so this was about ordered structure strengthening. And with that, we come to the end of this lecture. Thank you for your attention.